Assalamu alaikum. In the previous episode, we explored in great detail how gravity can benefit us. In this episode, we will learn how the formation of stars is induced by gravity, and we will also explore the various events that stars go through during their entire lifetime. My name is Hassan Ahmed, and I am your host for the show. Before stars begin to form, their initial form is called a nebula. You all must have seen in many pictures that there is a huge cloud with different colors inside it. Sometimes you'll see a bluish colored cloud, sometimes a reddish one, and sometimes different colors are mixed together and you see a cloud of that color. This cloud is called a nebula. These are what we call nebulae. They are found in many places throughout space. There is one nebula that you can see with your naked eyes without a telescope, but you can't see its colors. You just see a bright spot. If you carefully look at the magnificent constellation called Orion, the incredibly bright spot just below the distinctive belt of three prominent stars you clearly see is the breathtaking Orion Nebula, and that vast and luminous nebula is precisely the point where a brand new star truly begins its remarkable birth. The formation of a star happens in such a way that the nebula is a mixture of powder and dust, and within it there are different colors present. When these start to come together, collisions begin to occur among them. Gradually, over many years, they start to come closer and closer, and as they do, the particles begin to collide with each other. When you see anything collide, a lot of energy is released. There's an explosion, a blast. In the same way, when those particles start coming closer, a lot of heat is generated due to that friction. That heat keeps building up gradually over and over, and because these clouds are so massive, an enormous amount of heat is generated. Eventually, so much heat is produced that the phenomenon begins, which is called nuclear fusion. In nuclear fusion, two types of particles merge together and become a single particle. In this process, an intense amount of energy is released. So when this process starts, it also begins in every single grain particle, and the entire process of energy release rapidly takes off. Gradually, this process continues and heat starts to be generated, and nuclear fusion keeps going on. When this process continues for many years, its mass becomes so large that it starts producing its own energy, just like our sun. No energy comes into our sun from outside. It creates its own energy through nuclear fusion. It generates so much energy that even from such a vast distance, its energy reaches us here on Earth and warms our entire planet. This is the energy being generated. Every star does this. When you look at the night sky and see many bright specks, 99% of them are stars. The remaining 1% could sometimes be a planet or sometimes a galaxy that looks just like a star, but mostly they are stars. You might remember that in the first episode, we discovered that it takes a little bit of time for light to reach us. It can even take years. When light comes from our sun, we learned that it takes about 8.3 minutes to reach us. The stars above, the closest star to us besides our sun, is 4 light years away from us, meaning its light takes 4 years to reach us. This also means that when you look at that star, you're not seeing its present form. You're seeing what it looked like 4 years ago because it took 4 years for its light to reach you. Now that's just the closest star. The rest of the stars are very easily thousands of light years away, at least 500 to 1,000. So, when you look up at the night sky, you're actually looking into the past, because you'll only know their present state 500 or 1,000 years later. So if at this moment all those stars were to disappear, it would take us about 500 years to find out that those stars are gone. If at this moment the sun were to disappear or go out, we would find out after 8.3 minutes, because that's how long it takes for its light to reach us. This gap is much more noticeable with stars because they are thousands of light years away from us. Our star, which we call the sun, belongs to a category of stars that are actually quite small. There are stars much larger than our sun, and in fact our sun is one of the smaller stars among them, even though it seems big to us. There are stars so much larger than the sun that if you compare them on a scale, take the largest known star, VY Canis Majoris for example. If that star occupies an entire screen, then our sun wouldn't even take up a single pixel. To illustrate this, take a look at this infographic. Our star, the Sun, along with countless other celestial bodies classified as stars throughout the vast expanse of the cosmos, embarks on an inexorable journey of increasing its colossal mass as the eons gracefully unfold. This continuous accretion of matter is primarily attributed to the relentless gravitational pull exerted by these massive stellar entities, which constantly draws in and incorporates various forms of cosmic debris, including interstellar gas, dust particles, and even smaller planetary fragments that venture too close to their immense gravitational fields. As a direct consequence of this perpetual accumulation of material, their physical dimensions progressively expand, leading to an observable increase in their overall size and volume. Furthermore, this influx of new matter contributes significantly to their internal reserves of nuclear fuel, predominantly hydrogen and helium, which are the essential ingredients for the thermonuclear fusion reactions that power stars. With a greater abundance of this vital fuel, stars are capable of sustaining their luminous existence for extended periods, burning brighter and hotter. Concurrently, the internal pressure and temperature within their cores escalate dramatically, causing their heat intensity to continuously rise, radiating immense amounts of energy across the electromagnetic spectrum, profoundly influencing their surrounding environments and the celestial mechanics of their respective solar systems. Our star falls into the category that doesn't have the capability to become very large, but other stars, during their growth cycle, initially have a certain color. Gradually, as they continue to grow, their color shifts not just to yellow but also to blue, and after blue, it can even shift to red. Usually, these are the stars that are the largest. After that, there is also a category of stars that are completely white in color. These are the stars that have a very high intensity. The final stars, during their lifetime, don't just keep getting bigger. There comes a point when stars also die, when stars also have a death. How does that death happen? It's because there is so much mass and so much energy inside the stars that as they grow larger, they sustain themselves. Their gravity becomes so strong that there is a chance they might collapse under their own gravity and break apart. What this means is that they become so massive that their own force pulls them toward their center. So at any moment, they could collapse inward and fall in on themselves. So what stops this phenomenon from happening? When they are releasing energy, that energy cancels out this force. In other words, the force pulling them inward is matched by the energy they are releasing outward. When these two become equal, at that point, they start to resist gravity and do not collapse under their own gravity. But there comes a point when their fuel runs out, when nuclear fusion inside them stops. At this point, their gravity has become so strong that they begin to collapse under their own weight and mass, essentially breaking apart as they fall inward. Despite having so much mass, if they start to implode, such an enormous amount of energy is released that scientists call it a supernova explosion. A supernova explosion records temperatures that are not found anywhere else in the universe. This is the temperature that scientists call the limit, because we have never observed a higher temperature anywhere else. The energy created by this implosion is released all at once in an explosion, and these events are so massive and strange that you can even see them from Earth. They last for many years because they are so huge that the length of their explosion is so great we can observe them for years. You might think this phenomenon only occurs in very large stars, but it can also be seen in smaller stars. So what happens to them after the explosion? When a massive star explodes, sometimes all of its immense mass and scattered debris falls back together and ultimately forms an incredibly dense and compact stellar remnant called a neutron star. Its astonishing density is so extraordinarily high that if you were to carefully take out just a tiny teaspoonful from its incredibly compressed core, its astonishingly immense weight would be approximately a staggering ton. That means if you were to carefully pick up even a minuscule, almost imperceptible stone from deep inside this extraordinarily dense star, its substantial weight, its incredible mass, would be nearly a full ton. Such an immense and powerful gravitational force exists within such a remarkably small and incredibly compact star. But if the progenitor star is even significantly bigger, a truly colossal supergiant star, and it violently explodes, then what precisely happens next? When a truly massive supergiant star explodes, a completely new and utterly fascinating phenomenon occurs, which scientists meticulously call black holes. During this cataclysmic explosion, all the immense mass of the star comes together so incredibly closely that its colossal size dramatically shrinks down to virtually zero. Think of it this way: if our own sun, a relatively average star, were to become a black hole, when it powerfully exploded, all the stellar debris would come back with such an unimaginable and crushing force that it would compress and compress relentlessly until its size became almost like an infinitesimally small dot. the gravitational pull inside it would be so incredibly intense and overwhelmingly powerful that it would profoundly distort the very fabric of space-time itself, creating what we precisely call a black hole. We can understand black hole formation in much more intricate detail in a dedicated and comprehensive episode, but we'll explore black holes in even greater depth in the very next episode. I was your host, Hassan. Stay tuned for more.